Okay, so yesterday we graphed our exponential function. So we looked at our equation, we made our t-table, and we graphed our exponential functions on our coordinate plane. So today we are going to talk about how do we write our exponential functions from the graph, from tables, different stuff like that. So our first problem is we're looking at a graph of an exponential function. So they already give us the graph. Over here on the right side, they're telling us the different forms of our exponential functions, but we've seen these before. So this first form right here, a b to the x plus k. B is your base, a is the number in the front, and then we're adding some k value on the end. Okay, so our other form in the parentheses, we have 1 plus or minus r instead of just b. We've also seen this before, like 1, r is kind of like our rate that we've seen. So a, b, and k, we're going to talk about how we can find all of these different values. All right, so for part A on this one, we're writing the equation of the horizontal asymptote of the write the equation of the horizontal asymptote that the exponential function shown on the graph approaches. So horizontal, right, that's like a line that is straight like this. So if we're looking at our graph, you kind of notice that over here it like levels off on the end. So all of our exponential functions will approach what's called a horizontal asymptote. Now asymptote is just a fancy word for a line that it'll approach, but it never actually touches. So for this one, it looks like this horizontal asymptote is at 1. So all of our horizontal lines are y equals a number, because we're saying that this line y is always equal to 1 on that line. No matter what value of x, my y is always 1. So this graph is approaching 1. All right, so we're going to use that. So y equals 1, that's our horizontal asymptote that we're approaching. We're going to consider our equation, our form for our exponential function. We're going to substitute the y value the graph approaches but never reaches in for k. So k is always, so right here, this is k right here. K is always equal to the number that your horizontal asymptote is equal to. And then we don't know what a is, we don't know what our base number, our rate is for this one, but they did give us another point, 0.05 on the graph, so we can substitute that in for x and for y. So x is 0, so up here, this is x, our exponent, and then we're equal to y, so we're going to plug in 5 for that. So now this becomes an equation that we can solve. Okay, so I got, for part C, I got 5 equals a b to the 0 power plus my 1. And we're going to solve for a. Now, anything to the 0 power is 1. So us plugging in 0 for x allows us to make this 5 equals a times b to the 0 power is 1, so it's just a plus 1. So we're always going to use a point where x is 0 so that I can get a just times 1, so I just have a. So then all we need to do is subtract 1, so a equals 4. So for part D, it says discuss with a partner why the point 0.05 was used instead of -2.2. So like I said, when we plug in 0 for x, that gets rid of my b to the 0 power. That gets rid of my b, because b to the 0 would be 1. So if I used -2, like b to the -2, like I wouldn't be able to just get rid of that because I would still have my b. So we're always going to try to use a point where we can plug in 0 for x. All right, so next part says use the value of a, the horizontal asymptote, and the point -2.2 to find the value of b. So we know what our a is. We said that a was 4. And then we said we plugged in k, which is 1 because of our horizontal asymptote. And now we can replace x and y with -2.2. So b to the -2, and then I have y is +2. So now I've gotten rid of all my other variables, so I can just solve for b. So just to make this a little bit nicer, I'm going to write it over here. So 2 equals 4b to the -2 plus 1 is what we're solving. So first step, we want to try to get b by itself. We're going to subtract the 1 on both sides. So I get 1 equals 4b to the negative 2. And then before we do the exponent, let's get rid of that 4. So divide both sides by 4. So b to the negative 2 equals 1/4. And then there's a few different ways you can go about finishing solving this. We could either raise this to an exponent to get rid of that negative 2, or we can use our exponent properties. So remember, if we have a negative exponent, that would make this 1 over b squared, like it would force it into a fraction, and then the exponent would become positive. So then we have 1 over b squared equals 1/4. And then we can cross multiply. So we could do 1 times 4 equals 4, and then b squared times 1 is b squared. So then to get b by itself, square root both sides. So b equals 2. So our b is positive 2. Let me do this over here the different way, just to show you a different way to solve this. So b negative 2 equals 1/4. So thinking back to our radicals unit, we would get rid of this negative 2. We thought negative 2 times what would give me the positive 1. So we can do a negative 1/2 power. So we can raise both sides to the negative 1/2. This is also a way we can solve this. So b equals, that would cancel on the left and give me just b. And then to make this negative 1/2 positive, I would flip my 4 over 1, or 1 over 4 and make it 4 over 1. So then it become a positive exponent. And then changing this to a radical, 1/2 as a radical is the square root of 4. So we get 2. So either way works, kind of just up to you how you prefer to solve. All right, and then our last one, they want us to just write both of the formulas. Using both formulas, we have all of our variables, and we're going to just write our functions. So our first one, f of x equals a b to the x. So a is, we said it was 4, b is 2, raise that to the x, and then k is 1. All right, and then for our other form, we have f of x equals a, 4. Now in our parentheses, we don't know what r is, but we know that b is equal to 2, so that's equal to my 1 plus r. So to figure out r, we think 1 plus what is 2, which would be 1, so r is 1. So we have 1 plus 1 in the parentheses, and then plus 1 on the outside for k. All right. So I want you to pause the video and try this one on your own. So follow all the same steps on the top of your notes from the last one and try this one on your own. So pause the video, try it, and then I'm going to go over it. Okay, so going over this problem, our first step is to find our horizontal asymptote. So first step, horizontal asymptote, because that is our k value. So if we look on our graph, looks like it's approaching negative 4. So y equals negative 4 is our horizontal asymptote for this one. All right, our second step is to figure out what a is. So second step, find our a value. So we're using our formula y equals ab to the x plus k. So we know what k is now. K is negative 4, so I'm going to do minus 4 on the end. I don't know what a is. I don't know what b is. And then we're going to use the point 0, negative 4.5, because like on our first problem, we want to use the point where we can plug in 0 for x. And I will always give you a point when you're doing them from the graphs, like where they're, when 0 is x, is your x value, so that you can figure out what your a is. So we're using 0, negative 4.5, so b to the 0, and then we got negative 4.5 for my y value. All right, so we want to solve for my a, so I'm going to add the 4 over, and then b to the 0, remember that's just going to be 1, so it kind of goes away, and we just have a on the right side, and then negative 4.5 plus 4 is negative 0.5. So our a is negative 0.5. All right, now then the third step we did was to find b. So we're going to plug it back into this equation right here. We know what a is. We don't know what y is yet. Well, we're going to plug in some y value. Sorry. So to find b, we're going to do y equals negative 0.5, b to the, and we're going to use this to negative 8.5. So it'll be b squared. And then y value, we're going to replace that with the negative 8.5. Sorry, I'm getting squished, so I'm going to erase this. Okay, so we're plugging it into this equation. My y value is going to be negative 8.5. A is 0.5. B, don't know what b is, that's what we're trying to find. We're taking that to the second power because that's my x value and my point, and then plus your minus 4 on the end for k. And then we can go ahead and solve. So you're going to add the 4 to the right side, or to the left. So then on the left side, we get negative 4.5 equals negative 0.5 b squared. There should be a negative right here. And then go ahead and divide both sides by the negative 0.5. So my b's negative 4.5 divided by negative 0.5. Plug that into your calculator. You should get positive 9. So 9 equals b squared. And this one we can just go ahead and square root both sides. So b is 3. Okay, so they want us to write the equation in this form, ab to the x plus k. So we have our b and our a now and our k. So our final answer would be f of x equals, a is negative 0.5, b we said is 3, raise it to the x minus 4. That's your answer. All right, so that's writing from a graph. Now we're also going to do writing from tables. So instead of giving us a graph, they give us a table of values, so some x's and some y values. So we need to find a and we need to find b. So for this one, for part A, they just want us to describe how the values of f of x are changing as the x values increase by 1. So if we're looking at our table, all my x values are increasing by 1. Right? I'm adding 1 each time to these values. So we want to figure out how am I getting from one y value to the next. And remember, with our exponential functions, we're always multiplying by the same thing. They have a common ratio. So we've talked about this idea of a common ratio with our geometric sequences. So we're multiplying by the same thing each time. So to figure out how do I get from, like, let's do 8 to 20. We need to do 20 divided by 8. And that will be 2.5. So we're multiplying by 2.5 each time. And then you can check it, do 20 times 2.5 in your calculator, you should get a 50, and it should work each time. So for part A, we're going to say that our values of f of x, or y values, are being multiplied by 2.5 each time. All right, so our initial value A, we want to know what's our starting value. So your starting value for your exponential functions will always be when x is 0. So your initial value A, you can always look, so you want to look where x is 0. So we can look at our table. They give us 0, 8. So your initial value A will be the y value at 0. So it's going to be 8. So it's a little bit easier to find your A value if they give you a table, because if they give you x equals 0, then you know that's your starting value A for your function. So then for the last one, part C, we're just going to write our function. I think on your notes it just says write the function. So we're going to write our function in our form. So we need to figure out what B is. Now B is your common ratio. So we know A is 8. We got that right here in part B. Your common ratio is where you're multiplying by each time. So that's also easy to see from the table because we already figured that out. We already figured out that they're multiplying by 2.5 every time. So we already know that our function is going to be 8 times the 2.5 raised to the x. So if you're ever, like, once you get this function, if you're unsure, you could always, like, look back at your table and maybe plug in some numbers and see if you're getting, like, plug in 1 and see if you get 20. Like, that would be a good way to, like, check yourself once you finish and get your function, because it should match the table. All right, so for this one, I want you to try this one, pause it, see if you can do it. When you're done, play it, and I'll go over it. Okay, so for this one, they gave us another table. We're gonna see which, for part A, we want to know which ordered pair can be used to determine A, find the value of A in the equation. So on the previous one, we said whenever x is 0, the y value is our A. So it's going to be this 0, 3. So our A value is 3. And I'm going to prove to you like this works. So for this one, if we have y equals AB to the x, if we plug in 0, 3, so if we plug in 0 for x and 3 for y, so 3 equals AB to the 0, you would just get b to the 0 is 1, so 3 equals A. So it kind of, like I said, this is just proving you to where this idea of like when x is 0, that's just your A value for your function. All right, so for part B, if you notice the table, like it doesn't go by ones. So, sorry, it doesn't go by ones for the whole thing. It does go by ones from 1.5 to 3. So we can figure out our value of B by doing, by figuring out what do I need to multiply 1.5 by to get to 3. So you can do 3 divided by 1.5, which will give you 2. So we're multiplying by 2 each time. So our B value is 2. Another way we can do this, so say I didn't have this point right here and they still want me to find B. So we know what A is. So like right now my function is y equals 3 b to the x. We could plug in another value. So like say we could plug in 448 for x and y and solve for B. So like I can use the point 4, 48. So I'm going to do 48 equals 3b to the 4th power. And then I could solve for B. So I would do get B by itself, divide both sides by 3. So 48 divided by 3 is 16. And that equals B to the 4th power. And then we would do the 4th root to get rid of B to the 4th. So B equals 4th root of 16 is 2. So we get the same answer. So if your table is ever not going up by 1, it's a little bit harder to find your common ratio. You would need to find another point and plug it in for x and y and solve for B. All right, part C, last part, we're just going to write our equations. So f of x equals A is, we said it was 3, B is 2, and that's raised to the x. And then for the next one, we need to figure out what's going to go in for our parentheses. A is still 3. If my B is 2, I need to figure out 1 plus what gets me to 2. So R would be 1. So in the parentheses, I would 1 plus 1, and that's raised to the x. All right, last problem. So this is kind of just applying our exponential function. Okay, so we're going to be applying our exponential functions to like a real world application with this problem. Okay, so a migraine headaches affect 39 million men and women in the U.S. Excedrin In the U.S., Excedrin migraine is an over-the-counter medication used to treat pain from migraines and tension headaches. 2 Excedrin migraine gel tabs contain 130 milligrams of caffeine. Every hour, approximately 6% of the amount of caffeine in the body is metabolized and eliminated. So part A says, what is the rate of decay of caffeine in the body? So decay, that means like if something is decaying, right? It's going down, it's dying, it's not living, like so our ratio for this, like we're going to be decreasing each time. And if we reread this last sentence, it says every hour approximately 6% of our caffeine is metabolized and eliminated. So your body metabolizes the caffeine and then expels it from your body. So the decay of your caffeine it's decreasing by 6%. And they say every hour. So it's decreasing by 6% every hour. All right, so part B says, what is the initial amount of caffeine in the body immediately after taking the recommended dose of 2 gel tabs? So we see second to last sentence, it says 2 Excedrin migraine gel tabs contain 130 milligrams of caffeine. So if you take 2 gel tabs initially you're going to have that 130 milligrams. We can abbreviate milligrams with mg. So no time has passed. If it's immediately after you take it, that's our initial starting amount of caffeine in your body. All right, and then part C, they just want us to write a function. So they want C to represent the amount of caffeine in the body and T to represent the number of hours since you take your 2 Excedrin migraine gel tabs. We want to write C as a function of T. So normally we write like f of x, but they want us to write it as C of T. So we want C of T equals AB to the x. And for this one, if we're talking about rates, so usually with your word problems, we're talking about a rate that we're decaying at. Our B value is going to be we're going to be using the formula, the 1 plus or minus R to the X, because we know what our rate is. So that's going to give you the B in the middle. So for A, so writing this, C of T, A is our starting amount. What do we start at? So we said that was 130. And then for your inside of your parentheses, for like your common ratio, we are decreasing by 6% every hour. So to find what's going in my parentheses, I need to do, and I'm going to go over here and do this. I need to do 1. If we're decreasing, we're going to subtract. We want to do 1 minus the rate. So, and remember, we always change our percents to decimals. So 6% as a decimal would be 0.06. So we're going to do 1 minus 0.06. So in the parentheses, so that will give you 0.94. So it'll be 0.94 for in our parentheses. And then we're raising this, and we're not using x. Sorry, we're going to be using t, because t is kind of representative of our time. So if this were like an increase of caffeine, then we would do 1 plus the rate. But since we're decreasing and we're taking away that 6% every time, we want to do 1 minus the rate. All right, so this is our final answer.